Thank you, Pam. Thank you for the wonderful talk. I'm not Biswa, so if you look in your program and you saw some really interesting titles and some interesting things, I'm not that, but hopefully it can be interesting to you anyway. I'm going to be talking about channel capacity and dropout, and most of this is not my own work. In fact, most of this is from the ground up, so I'm going to go over a review of deep learning, some feed-forward neural networks, if you happen to skip the Sunday educational sessions. And then we'll get into channel capacity and a little bit about some ideas of interpreting what dropout might be doing. Right. So first off, a plug for our own lab. IGC, which is where I work, is hiring postdocs, grad students, whomever. So contact Ned Jahanshad or Paul Thompson if you are interested, or me. So right, deep neural networks. So this is going to be fast if you skip the Sunday session. We have an input layer, some hidden layers, and an output layer. And what's going on? Your inputs, we're just going to treat them as a vector, and you transform them onto the blue hidden layer, and then you do a nonlinear element-wise transform and transform them onto the red layer, right? And then do another nonlinear transform, and yeah, that's it. Then you start stacking them because you want to do deep learning, right? You stack them again, and it gets very complicated, and so you put a black box over it, and you never see inside. And just do inputs and outputs. So that's our 30-second cognitive model of what a deep network is. And clearly here we've stacked too many layers, or so many layers that we just have to black box it. And we can really view them as function approximaters instead, just very flexible function approximators with a large number of parameters. So here, we have, well, there's a 25 by 25 matrix, and this is just a toy example, between every layer, right? So that's going to be a lot of parameters. How do we train them? So this is actually relevant to dropout. So you put in an image, or you put in whatever, and then you come out with some probability of what it is, and you can generate an error from this. So this is a tennis ball, so you want the probability of soccer to be low, and the probability of a tennis ball to be high. And right, then you propagate this gradient. So you take a derivative, and then you do the chain rule over and over and over again, and so on, and you can propagate these gradients. So in a nutshell, for this short review, deep learning is really stacked linear transforms, or feed-forward deep learning is stacked linear transforms, and then nonlinear element-wise transformations. So just combinations of that over and over and over again. And there's a large menagerie of different architectures that go beyond this, but at least for dropout's sake, or for the content that I'm going to talk about in the remaining 10 minutes, you don't have to think about that. We just need to think about this feed-forward model of trying to classify a tennis ball or a soccer ball, right? And we back-propagate error. So we're using the chain rule, and it'll just flow backwards through the network. So with that, let's talk about what we really came to talk about, some dropout. So what is dropout? Dropout is a master's thesis from 2012, 2014, which wouldn't we all be so lucky, right? And essentially, it dictates masking neurons at every step. So we're going to apply a binary mask to all of those blue neurons that we saw earlier, and some of them are going to be zeroed out. And usually, so that's it, right? That's the end of the explanation of what it is. And usually, it gives a small performance boost, which is mysterious, right? It usually meaning across a wide variety of models and across a wide variety of contexts. Now, it's not the end of our computation. It's not saying like, oh, we can solve everything with dropout. But it gives a small boost most of the time. And that's strange, right? That such a seemingly silly task, like putting a binary mask into our network and removing nodes, gives us a boost. This paper was rejected from NIPS, so Neural Information Processing Systems, top machine learning conference. It was rejected in 2012 and propagated solely as a preprint on arXiv, and then was a tutorial in 2016, I think. So that should tell you something about its acceptance, or maybe give us hope for all our rejected arXiv-only papers, right? Right, so what does it look like? So we're applying binary masks. Every time we train this network, we remove some nodes. So now we have this strange looking network that if we coalesced it, it would be bumpy and have some weights missing. And we resample this mask at every step, so when I train it again, I'll have a different, well, quote unquote, different network. But of course, if we go back a couple of steps, we really have these weights that are underlying the whole, that are underneath the whole thing, and it's not as though we're training completely new weights every mask sample, right? We're only just resampling the binary mask. So, right, so it's like as though we're generating new, quote unquote, new networks every time. And this intuition leads us to a couple of explanations of what might be going on. So the popular one, oh, sorry, first some results. So this is the only result in the paper, that it works better, it gives you a small boost. So this is on an MNIST dataset, the classic machine learning one. And right, so without dropout and with dropout, you get what looks to be about a 1% boost. MNIST is pretty easy, so maybe on yours you'll see 4% or 5%, but it's not going to change your life, but maybe it'll change some good results, or, I mean, it doesn't hurt to try it out. Right, so some ideas on why it might work. We were seeing those networks that were resampling, essentially. So we have these resampled, topologically sorted feed-forward networks, and you could think about this as training different ensembles, or training an ensemble of different pseudo trees or almost trees, right? That we have a whole bunch of these models, and they are all closely related, but really there's just a family of them that we're resampling from, and the weights underneath are they're defining the family. Some other people came along around 2013, 2014, and started thinking about it in a Bayesian sense, that it's really from that family, we're defining a model uncertainty over the possible models that could come from our, in this case, feed-forward network. So there's a whole bunch of sub-models in the network, so any viable paths from input to output, right? And those sub-models, we're defining an uncertainty over them and resampling over and over again. So that's what that's how they interpret it. And our interpretation will be slightly different, that we're going to come at it from an information theoretic standpoint. But it's the same idea that we're talking about channel capacity. So I guess I'll show that in the next slide, but what I will propose to you is that dropout essentially is a regularizer on the amount of information, so the complexity of the model that can be pushed through this structure, this feed-forward network. Most of these explanations are not mutually exclusive. So there's no right or wrong, at least in this case. You can interpret it, there might be wrongs, but there's not a good way to say that somebody's right for certain. That we can both believe the model uncertainty, the model selection idea, and also this channel capacity idea, and perhaps even pseudo-ensemble methods, and some of the stranger biologically inspired ideas that they proposed. We can believe many of them, or all of them actually, at the same time and still use dropout. So it's just one view of looking at it's just one way of looking at the world. Right. So what is channel capacity? If we're sending a message, so we're sending X, I'm talking to Pamela, for example, and I send a message X, and it goes across a noisy channel, like in this room. There's echoes and all sorts of strange stuff. The channel capacity is the total amount of information I can send to her. So in this case, it's pretty clear, but if I was sending across like a telegram across the wire that's really noisy and across the United States or something, or Australia, then maybe the capacity is much lower. And this depends on the noise in the channel. So it's the amount of information you can push across the wire, or the mutual information between what I send and what she receives, right? And you can decompose this into the entropy of the received message, and then the conditional entropy of the received message conditioned on the sending message. You can also do it symmetric. This decomposition is symmetric, so it could also be the entropy of my sent message, and then the conditional entropy of the received message, right? So dropout, at every step, we send a hidden unit through a noisy channel, a very simple noisy channel, one that either blacks it out or does nothing, and then that reduces the amount of information we can transmit through the network. And in fact, when you do the computation, which I removed because I was scared that, well, you wouldn't be able to read it because it takes a while. But if you do a lot of algebra, it turns out that with no dropout, it's pretty simple. It's the amount of information you can send. But it scales linearly, like directly, with the dropout probability. So the channel capacity just goes straight down. Now, this is in a very simple model of neurons, where they're either -1 or 1, right? Very simple model of computational neurons even, right? So even in our computational reality, they're continuous, and continuous entropic measures are problematic at best. But the intuition remains that as I increase the dropout probability, I'm simply pressing on this channel capacity, and I will not be able to send as much information across the wire. So what does this look like in our network? Right, so for a dropout probability of 50%, my channel capacity is now 2.5. Well, of course, these neurons are not fully independent, so it's not as though we've flushed out the whole capacity in the first place, but we're well over-parameterized for a channel capacity of 2.5, right? If we are only able to send 2.5 bits using 5 bits, right, this seems interesting, extreme, perhaps. And I think this idea of over-parameterization also occurs in many other in many other engineering disciplines and in many other biologically inspired engineering disciplines. So for example, in robotics, when they're parameterizing arm movements, robotic arms, they often over-parameterize the servos because if you exactly parameterize them, you'll break the arm because there's only a very small acceptance region. And the same might be the case here. Other examples of over-parameterization occur quite often in math and in optimization, where you add slack variables or auxiliary variables, and you're able to give yourself some space, right? But either way, there's a complexity penalty on the model complexity, but no structural constraint. And as Pam explained earlier, the meme, if you will, of neural networks is just this pyramid-like structure that goes and slowly condenses the information down in a bottleneck sort of sense. But here we're able to do it a little bit without changing the structure at all. So that, to me, seems relevant for explaining what dropout is doing. Right. So a little recap. Dropout gives a mild improvement to most models, and a mysterious mild improvement, but it's not going to change your life. On the other hand, it's really interesting to think about that why would such a silly, or why would doing this binary mask game actually help you? That's something to think about. It's very easy to implement. In fact, it's built in most modern neural network methods. So TensorFlow, PyTorch, whatever you want. Yeah, it's already there. And it can be interpreted as a stochastic regularizer on model complexity. So if you think about linear regression, for example, we have L1 regularizers and L2, well, we start with L2 regularizers and L1 and elastic net and all kinds of things. And those are all regularizers on the effect size almost, right? The weight size, of the size of the weight vector. Well, this is a direct regularizer on the complexity of the model, which is what we wanted to do with L1, right? We wanted to reduce the support of the weights. We wanted to use L0 essentially. We wanted to remove all the weights that actually weren't relevant, but we couldn't do, at least not particularly efficiently or easily until we got a lot of new maths. So, right, so this channel capacity idea is also reflected in a paper called The Information Bottleneck, which was not originally a deep learning paper. It's by Tishby and Naftali in 2000-ish. There's some controversial belief that it's relevant to deep learning, but it's certainly an interesting paper, and I suggest you take a look at it. There's an updated version for the deep learning age about 2 years ago, or 1 year ago now, 1 or 2 years ago. And there's a variational version, so that's fun too. But these are all stemming from this channel capacity idea that we could reduce model complexity using channel capacity. yeah, that's all I have. So thanks for listening. Sorry, I'm not Biswa.